Next instruction is called return. We have one unconditional return and these many conditional returns. For you to better understand what this is, I want to give the same example that we've been talking about. Let's say that we said in the previously we said that the last instruction, the last part of the PC was that it was loaded with A0F5, which was this memory cell, and let's say that this was some instruction. All these instructions were getting executed, and as we previously explained, these set of instructions are called the ISR, or interrupt service routine, the program or the function that would get executed when we called to this location. Now this interrupt service routine has been executed until we reach the C12B. We know that this is supposed to be our last instruction, but the CPU doesn't understand. The only thing the CPU understands is that PC is C12B, and it would do the same thing that it has been doing all along. It would put this value on the address bus, therefore this memory cell would be selected. So the data of 1000000 would be read, and we are now, well, the fetch machine cycle has been executed. Obviously the PC would be pointing to the next location, but that doesn't matter. Even though, let me actually write it down. So 011, we get to 100, but the length of this instruction is 1 byte. So here, as the CPU is in the decoding of IR, it understands that this instruction is just like pop PC. Meaning, even though we don't have a pop PC, this is called return, but it is equivalent to that. And we already know that what this operation does is that it would say whatever SP is pointing to should be put in some place. Then SP should be incremented by 1. Then whatever SP is pointing to should be read in another place. Then SP should be incremented again. Now, what do we mean by these places that we are saying? The argument is PC, which is 16 bits long. 16 bits mean 2 bytes. One of them should be the higher byte, one of them should be the lower byte. The logic in 8085 says lower byte, lower address, higher byte, higher address. The SP is incrementing, which means that the first one would be the lower byte. So here would be the lower byte of PC, and here would be the higher byte of the PC. So one by one step at a time, like always. We are whatever SP is pointing to. SP is pointing to F055. So again, this value would be put on the address bus F055. We are here. The value would be read, which is this value, inside the Z register. You see, you just follow along all the steps that you have written here. So we would have the value of this is 03 in hex, and then SP would be incremented again. Let me change the color. So from F055, I'm just changing the hex to F056. Then this value would be read inside the W. We have 10, and SP would be incremented again. We have F057. Now WZ with the same format would be written inside the PC. Now we have 1003 here, or 0001, 0000, 0000, and 0011. Obviously, you could, if you only want to understand what happened, you could just directly say what is happening, but we are just working with the WZ registers. So again, with the same logic that lower byte, you could have said this, that we have an address in these 2 bytes, right? We have the values of 03 here and 10 here. Which one is lower byte and which one is higher byte is like this: lower byte, lower address. So F055 is the lower address, therefore 03, the contents in this memory cell, this would be LB, and this would be the HP 1003, therefore this would be written, this will read by the CPU inside the PC register. 1 fetch, right? And 2 reads have been done for the return instruction to be executed. What is the equivalent result? The what is the outcome of the execution of this instruction? It was that now this value is pointing to 1003, which means the CPU would do everything that it was doing, put this value on the address bus, would read any content that it is in the 1003. From your perspective, the CPU has been executing a program. Then an interrupt happened, CPU jumped to the beginning of that ISR or interrupt service routine, or the function which is supposed to get executed when the interrupt happens, has completed the execution of that interrupt, then has come back to whatever it was left off. This is what you are seeing, but the CPU is just doing the same thing that it was doing all along. For those of you who actually got one of my courses called Reverse Engineering and Exploit Development, we talk about exploit development in Linux, reverse engineering and exploit development in Linux. We absolutely talk about what is security, how you could use this as a vulnerability and do some exploit with it. You could somehow understand that when the interrupt, the ISR completes here, how you could change the return address here so that the CPU, after completing the ISR, it jumps to another location which you have put a virus there. But as I said, that course is actually my longest course, which is about 18 hours long, and everything about the security has been explained there, including some of the things that has been explained here. So this was the return address, and finally we get to RSTs. These are called the software interrupts. What are these instructions? These are just, we said that call and return is a combination of interrupts that we see as interrupts. These RST is exactly like a 1-byte call, meaning that, let me just actually put the format of RSTs. This is actually the format of all these instructions, which means that 11000111 would be for RST0, which is C7 in hex, and the last one would be 1111111. You see the first two ones and the last three are common in all of them, and then these three would obviously be all ones for this. This is the last instruction or last bit pattern in 8085, which in hex would be equal to FF. So FF is the opcode for RST7. What are these instructions? This says call to the location of 00. What is this? This says call to the location of 08. This says call to the location of 10 in hex or 16. Whatever its argument is that we are seeing here would be multiplied by 8, and it would do a call to that position. What is this one? Obviously, if this is 16, the next one would be 24. This would be the 24 in decimal, which in hex obviously would be 24 divided by 16 would be 8. So this would be 18. And after 24, we get to 32 divided by 16 would be 2, right? 20. So this would be call 20. This RST5 would be 5 times 8, call 14 decimal. Again, 14 decimal is 2, 40. You know, when you want to convert the decimal to hex, you say 40 divided by 16 is 2. We have 8 as the remainder. So we have 28 as the hex equivalent hex. 6 times 8 is 48 divided by 16 is 3, and the remainder is 0, right? So this would be 30. And finally, 7 times 8 is 56. So you could do the exact same thing, which would be 348 and 8. This would be 38 in hex. So 46 is actually 38 in hexadecimal. What is the benefit of using RST instead of call? Well, the good thing is that the length of the instruction is 1 byte, meaning that the address is already implied in the opcode. Where? Well, you just saw using the argument here, which argument is these 3 bits here. 111 is actually 7, 000 is 0, the opcode for here. So these 3 bits here are the implied address that the CPU should do a call to. Why can't we do this for all these call instruction as well? Well, you don't need me to explain it to you. We have 65,536 different addresses. If you divide this value by 8, why? Because the difference between all of these things are 8, because we want to put some instruction there to jump to our corresponding ISR, right? We don't want to just say call 00 and then call 01, because we can't put any instruction in one memory cell. Therefore, there is 8 byte left in different memory cells. Now, if you might have said, even though I highly doubt it, that why can't we imply all the addresses as the in the opcode, so that the length of all call instructions are 1 byte. What I want to show you is exactly how many opcodes we had to have in order to do this. Well, we wouldn't need 65,536, because we are leaving 8 bytes, 8 bytes in between, right? So we say 2 to the power of 16 is this value, divided by 2 to the power of 3, which is the length, the distance between two addresses. It would be equal to 2 to the power of 13, which is 8 kilobytes. So you had to have 8,192 opcodes to imply all the different addresses with a difference of 8 bytes for you to have 1 byte call instructions. But well, we only used 8 3 byte instructions for our call instructions, and also 8 RSTs for 1 byte call instructions. Just call them RSTs. They don't have any difference with these call instructions that you are seeing here. Anyways, you know that the way that you are using all these call instructions and return instructions, they are alongside each other. That's why I decided to explain them together. See you in the next lecture.